This video is for class 9 physics, and today we are discussing speed of sound in different media. It is our common experience while standing at some distance from a blacksmith that when a blacksmith strikes his hammer on an iron nail or iron piece, the sound produced on striking the hammer is heard a short while after the hammer is seen striking. Similarly, the sound of a cracker is heard only a little later than it has exploded. That is when the flash is seen. This indicates that sound does not reach us instantaneously, but it travels in a medium with a finite speed, and it takes some time to reach us from the place where it is produced. So that's why it has wave velocity, right? So the speed of sound in a medium depends upon the following two factors, right? So when the sound is traveling, okay, these two factors affect the speed of sound. The first one being the elasticity E of the medium. Here the word elasticity means the ability of the particular medium or the particles in the medium to move apart or to go away from its original position and then come back to its original position, right? So elasticity, don't get confused it with stretchability, right? It's not only stretchability, it is the ability to come back to its original position after being stretched. When the force is released, then it should come back to its original position, which is denoted by capital E of the medium and the density rho of the medium. So these are the two factors which affects the speed of sound. So the speed of sound needs to have a formula including these two factors. So the speed of sound will be equal to under root E upon rho, where E is the modulus of elasticity. Now the term modulus of elasticity, you learn this in your higher classes, right? For the time being, just remember it is the positive value of the elasticity, right? A numerical value of the elasticity which is positive. Then it's also called Young's modulus in case of solids or bulk modulus in case of fluids. Now what is Young's modulus and bulk modulus, you'll study afterwards again in your higher classes, in class 11 12 probably. And rho is the density of the medium, which you already know. Newton assumed that when the sound travels in a gas, the temperature of the gas does not change, right? That is, the propagation of sound is an isothermal change. That means whenever the sound is traveling in a medium, the temperature of the medium should not change. For isothermal change, modulus of elasticity, that is E, is equal to the pressure. So we can write E equals to pressure. Now whose pressure? That is the pressure on the medium in which the sound is traveling. Thus from equation 8.4, the speed of sound in a gas takes the form V equals to under root P upon rho. For air at normal temperature and pressure, P equals to 1.01 into 10 to the power 5 Newton per meter square, and the rho's value is 1.293 kilogram per meter cube. So V comes out to be 279.5 meter per second, but experimentally the speed of sound is in air is found to be nearly 330 meter per second. So you can see here there's some difference in the values of the speed. This is from the experiment, whereas this is from the formula here, this one, right? So that means this formula is having some kind of problem, something is missing in this formula. Thus the speed of sound calculated by using equation 8.5 is found to be lower than the experimental value. So later on, the scientist Laplace applied a correction to the above relation. According to Laplace, when the sound travels in a gas during the formation of compressions and rarefactions, there is no exchange of heat in the medium. That is, whenever the mechanical energy of the vibration is being changed into other forms of energy, it is not changing into heat energy, right? When the vibration is changing into sound, no heat is being produced. Thus we can say the propagation of sound is an adiabatic change. Adiabatic change means there is no heat energy being produced from any other forms of energy. Whenever there is a change of energy, right, heat energy is not being produced. For an adiabatic change, modulus of elasticity takes a new form, which is E equals to gamma p. Now the alphabet, this one here, the Greek alphabet is known as gamma, G-A-M-M-A, gamma, or GAMA, simple, right? So where gamma is the ratio of the specific heat at a constant pressure to the specific heat at a constant volume. Now this gamma also is having a value, right, which is equal to Cp upon Cv, where Cp is the specific heat at constant pressure and Cv is the specific heat at constant volume. This specific heat you learn in class 10, right, but we shall not learn in constant pressure and constant volume, etc. That you will do in your higher classes. And P is the pressure of the gas. Hence the equation 8.4, the speed of sound in a gas is given as V equals to under root rho p, gamma p upon rho. The value of gamma depends on the nature of the medium. For air, gamma's value is 1.4. So I hope you are understanding this. Okay, in this what we are learning is how does the equation is changing and getting its new formation, right, getting its new form, so that we can match with the value from the experiment. So the modified formula, that is equation 8.6, give the correct value of the speed of sound at the normal temperature and pressure in air, taking gamma equals to 1.4, p equals to 1.01 10 to the power 5 Newton per meter square, and rho equals to 1.293 kilogram per meter cube. V comes out to be nearly 330.7 meter per second, which agrees with the experimental value. That means this formula is correct. Now the speed of sound is different in different media. The speed of sound is more in solids, less in liquids, and least in gases. Since solids are much more elastic than the liquids and gases, that means the solid molecules has the ability to come back to its original position, right, more properly than liquids and gases. So the elasticity of the solids are more. The speed of sound is nearly 5100 meter per second in steel, 1450 meter per second in water, and 330 meter per second in air at 0 degree Celsius. Table below gives the speed of sound in different media at 0 degree Celsius. So speed of sound in some media, gases, air, carbon dioxide, hydrogen, the speeds are given. This table is not so important. Okay, once you can just go through if you are interested. Otherwise from the examination point of view, it doesn't have any role to play. We just need to know the speed of sound in air. That too it changes, right? There are certain factors which affects the speed of sound in the air, that we'll understand afterwards. Examples showing that the speeds of sound in steel is more than that in air. Number 1, if sound is produced at one end of a very long steel bar, two sounds are heard at the other end. One which reaches first is propagated through the steel, and the other which is heard later is through the air. Number 2, a person living near the railway track often presses his ear against the steel rail to guess whether the train is coming or not. The reason is that the vibrations produced by the moving wheels of a train travel much faster through the steel rail than through the air. So sound is heard through the track much before it is heard through air. Thus the person, by hearing the sound through the steel rail, gets an indication of coming of train well before its sound is heard through air, right? So this much for this video, right? I hope you have understood this particular part. If you haven't, you can always ask me the question in the comment or in the Google Meet.